for things with like a user interface, for example, this is extremely important because your tail latency can be like how long it takes for the page to load and that sort of thing. And there's all sorts of studies that if you take too long, users check out or don't use your system. And so that's why we want to focus on this. But we also care about doing this in a way that's cost effective. And this is especially true like these days. Maybe 5, 7 years ago, companies were very comfortable just throwing money at the problem. And so you would solve your tail latency problems by just like throwing as much hardware as possible at it and just be super over provisioned. To be cost effective, though, we want to be able to have those same latencies while having just like the over provisioning that's necessary. And then we'll use that over provisioning for failure tolerance and for some of the work necessary to make our tail latencies better. So the paper talks first about why we get this variability in tail latencies. So some of those include we're sharing these machines often, right? So either we're sharing them in the cloud these days, and so we have literal noisy neighbors because you're on one big box and you've got maybe a few CPUs and another person has other CPUs, or you're co-locating applications, like maybe you're running Kubernetes or something like that. And so you have multiple applications on the same box, or you're just literally deploying applications on the same box. There's also background work going on. So, maybe like compacting and uploading logs, disk management, all those sorts of things. And those can introduce variability as well. Maintenance, queuing, power limits, if you use a garbage collected language, garbage collection, but all of these things introduce this variability into the system. And that's where you start to see impact on these tail latencies, right? So we get a bunch of throughput leads to a bunch of GC on your JVM or in Go or something like that. Or you get a bunch of queuing and your tail latencies go up as a result. And so that's what we're looking to solve, or not like solve as in get rid of these problems, but solve as in work around the fact that we can't get rid of these various problems.
Let me interject real quick.
Yeah.
I'm pretty sure everybody in this room is aware, but just for the YouTube audience, Jordan's talking fairly advanced stuff. Fundamentally, just tossing money into having more machines, you're going to increase your throughput, but not necessarily tail latency. So you have to understand all this if your goal is to make sure no user is suffering from slow pages loading and whatnot. Back to you.
Yeah. No, that's a great call out. Thank you, Dima. So yeah, like you can keep throwing money at the problem, but at some point throwing money will have diminishing returns and you'll just be basically burning dollars with your CPUs. And so again, all these different things can contribute to that latency. And the easiest way to think about it though is like computers do stupid things sometimes and you have to account for those. And so the paper talks about in like over the course of a whole page, if you'd like to read it, like more detail about why those things happen. But really what all of this is set up for is to say like, look, we have to live with this pain. Computers have to do computer things. And so we have to instead be smart about it. And the reason we have to be smart about it is largely depicted by this graph. And let me zoom in a little here. So if your computers are going to do bad things, the more computers that you have, you actually increase the probability that a request happens during one of those bad things. So this is sort of counterintuitive at first because we usually think like more computers better, but in this case, more computers means more chance for bad. And so this blue line is your probability when you have 100 computers of hitting a problem. When you have 1,000 computers and when you have 10,000. And so we want so we can add computers to reduce the probability, but we can't actually not hit the problem. And then because of let's say 18% of 10,000, your chance now of actually hitting the tail latent problem goes up. And so we can see here Also, like looking at these graphs, how different tail latencies can be, right? So our 99th percent latency is over 3 times our average latency. And that's why it's more interesting to look at our tail latencies. So all of this part of the paper here, these first few pages, is just really sort of setting up the whys behind like putting in all this extra engineering effort. So from there, the paper breaks down techniques into 2 groups. One is how we handle single requests. So how do we make one request have less tail latency in its own sort of like silo? And then the other one is what can we do across requests? Can we do not necessarily at the request level, but at like the system level to smooth out these bumps in latencyy. And so we'll start with the techniques for single level requests. And that is hedge request, tied requests. So I'll leave it here on this graph for now. So some of the techniques are application dependent. And so like in Google's case, what they did is they looked at the kinds of requests that flowed through the system. There are some that were interactive, and then there were some that were more like background requests, like maybe like a system in the background, etc. And so they determined that they could prioritize between these 2 requests, right? Like the requests that a user is doing where you have this, like again, sort of scientifically determined human behavior of like when things are slower, we get impatient and we move on. We want to prioritize those. And then computers who care less and don't have like a concept of patience, it's okay if they wait a little bit longer. And their works in the background is not like necessarily like, if it takes 100 milliseconds or 200 milliseconds, the point is the background work needs to complete. But that difference in latency doesn't matter. But for the human, we want something loading in like 10 to 50 milliseconds, so the latency does matter. And so the first thing you can do is sort of classify your requests and prioritize them. You may say like, well, I don't have that kind of problem. There's a whole bunch of different ways that you can classify these requests. So one way recently that I saw this in my day job is an application has 2 types of background requests. One is kind of like a data integrity request, and one is like the main low latency sensitive request. And I can only share so much details on what those requests do, but sufficient to say like one has to be really fast, and one, it's more important that it succeeds, but we don't care how fast it succeeds. And previously, they would both enter the same queue, and so you would do like the expensive thing, and all the things that you need to go fast were waiting for the expensive thing to complete. And so that's suboptimal and introduces more latency. So what we did was just split those out into separate queues, and then we prioritize across the queues. So just like this paper.
Let me confirm real quick. This is about your own application server, right? That's your custom code. That's not a load balancer level, nothing on that at that scale.
No, this is actually built into the system uses Cassandra as the database. So we actually modified Cassandra to do this prioritization or this multiple queuing. So it's not the exact technique here. The technique described here is to use one queue with priorities because we only had 2 classes of request, and in the real world, you have to, prioritize speed of development, etc. It was easier to just prioritize 2 queues and just always check if the queue you care about more is not empty, then service it. And if the queue you care about less, if that one is empty, then you go to the queue you care about less. So there's different techniques, but yes. And the reason for sharing this is to say, these like this paper written in 2013, the techniques from it are still being used heavily in production today in 12 years later in 2025, just in slightly different forms. So that's the first technique, is just classifying and prioritizing requests and basically saying the things that need to go faster, we should do first. There are considerations to this, like you can starve the slower stuff if you get enough of the faster stuff. And so that's why like the technique that is described here in the paper using priority queues is better than the technique I described in like my real world application where we just like had 2 segmented queues. But the goal again is just to think critically about your application and say, oh, I'm going to make the more important things actually more important in my system.
Two queues are a corner case of a priority queue. That's perfect.
Yes.
That's a perfectly correct statement. Yes.
Yeah, exactly. Any questions on the priority queuing technique before I move on to some of the other techniques? I know this can be a bit dense.
Yeah, Jordan, you mentioned that you have a prioritization in Cassandra implemented. Do you have plans to share it with community back?
I have to actually ask. Oh, yeah, and Dimitri, I guess
yeah.
a little bit more color for you. We prioritized each quorum requests behind everything else because we had an application that did each quorum and local quorum, and so the expensiveness of the each quorum requests, that's why we put them on a separate queue.
Yeah, because we have a very similar issue when we have some first priority applications and second priority applications which are working with the same Cassandra cluster, and we would like to reduce impact from the second application set to the first one. And unfortunately, as of now, Cassandra doesn't have out of the box the prioritization logic, so you have to. The best way how you can handle it now is to split it like to different data centers to avoid, if you want to avoid impact, and it would be really nice contribution.
I will talk with the team. And for the other folks, just to add some background. So Cassandra has sort of different expenses to their requests, and you have a Cassandra cluster spread across the world. You can tell it to just talk in its local area, like in Seattle, let's say in like the US West data center, or you can say, I need the request to be propagated like across the world. And so that was my expensive request. In Dimitri's case, Dimitri also works on Cassandra. He's talking about different applications having different priorities and wanting to segment those. So a lot of different ways that we can apply this technique.
Let me ask one more thing, just
yeah.
terminology wise. What's the 2025 standard? You could call it a quality of service, QoS. I sometimes use the term throttling for like second, third tier requests. What's the correct way to call them?
I think like probably QoS. I honestly call it like priority queuing. But I think like if we look to the literature, we would look to networking, because networking is like the area I think of our industry that has done this the best, and they call it QoS for quality of service.
It's just, I might be going ahead of ourselves, ahead of you in this case. It's just eventually if it's a user-facing request, there's a good chance that it has to be stored within, let's say, like 2 seconds, or it's best to be dropped. So that's a different philosophy in handling the other queue, right?
Yes, and so that is a different technique. We talk a little bit about that technique a little bit later, but it's not actually super covered in the paper. But I will talk about it really quick and how Cassandra does it, which is Cassandra records when it gets a request, and if it pulls a request to work on off of the queue and it determines, hey, this is already past the timeout, it just throws it on the floor and basically fails the request. And I would call that more of like a work shedding approach to things.
Let me add one more thing real quick. Go on, sorry.
Yeah, I want to highlight one more thing. We are speaking here about queues, but in frequently, it's not necessary to keep your request within a queue. You may use some other structures, and I can share, I'm not sure if is it covered or not, but there is a similar article which calls fail at scale from Netflix about using some alternative ways to organize your input queue data. Instead of FIFO, you can use LIFO, or you can use some more complicated techniques like coder-like things to drop requests earlier from the queue. It's a bit similar to request that time, but also have some extra ideas. I sent a link to the chat.
Thank you. It's been a minute since I've read that article as well. But yeah, so there are a whole host of techniques to do this like better, but the general idea again is segmenting and prioritization, as well as work shedding. Cool. So
let me add one practical thing, and also it relates to David's question before. So hey David, what we did a long time ago, which might be a good trick still, is you literally have a service with 2 different ports to serve different QoS requests. and they go to different load balancers on Amazon. And if the service is slow in one of the queues, it declares itself unhealthy for this particular subservice, and the load balancer does the rest. So that's actually quite a simple, neat trick to still maintain low enough tail latency for tier 2, tier 3 requests.
Absolutely. And yeah, sorry, I missed that question in the chat. I'll keep the chat up. But yeah, so David, also like in the case I was describing with Cassandra, we tag the request by knowing what Cassandra calls the consistency level. But we know like if it's asking for that global request or local request. And then like Dimitri's case, he's talking about various applications, and there'd be some way to identify, you know, application A versus application B, whether it be like IP address or something in the protocol. If you're doing HTTP requests, like, yeah, you can tag it with a header, but there's a whole bunch of different ways, but you'd need some way to differentiate type A from type B. So the next technique they call time slicing. And the idea with time slicing is that you take something that's expensive and you break it up into sub jobs basically to execute, so that it's not hogging the resources for entire chunks of time. That makes these long running things more latent, but it makes your low latency things less latent. So you're making this trade-off and this choice between something expensive and something and something that you need to do quickly. I don't actually have great examples of an application that I've worked on doing this in the real world, but the best way that I could sort of make a parallel to it is like when you do asynchronous programming with something like G-event in Python or reactive programming, where when you need to block a thread, you don't block the thread, you yield and you do the thing in the background, and then you take the thread back when you're done. It's a similar idea. You know, Google was working on like MapReduce jobs and things like that. So for them, like the MapReduce job may be on a node that's also a database node. And so you kind of like do part of the MapReduce step, and then you do a little bit more of the MapReduce step, but you're yielding the CPU to the database more regularly. So that's sort of the shape of these. But the idea is to take some large body of work that would take a really long time and break it up into chunks where you can yield over to the other work being done on the machine periodically. So like if you're writing a file, writing in blocks and flushing the blocks in the background, that sort of thing. Questions, thoughts on head of line blocking? I know that one's a little bit short, but again, I only have so many real world examples of that. Cool. We'll move.
I would add that realistically, if you care about tail latency, you should be using yields a lot, as in green threads as opposed to kernel threads. And I assume everybody knows this. Like the entire Golang exists because Google said this has to be a standard.
Yeah. Unfortunately, I work in Java, and they just got 3 green threads, and so we're usually doing this ourselves. But yes, if you have a language for which that's a first class citizen, use it.
But Java now has virtual threads, Java 21.
Yes. Yeah. Cassandra is back in the like we just got Cassandra off Java 8. So, but yes, we would very much love to be on 21 and get to take advantage of a whole host of things that are better.
Yeah, but you're old-fashioned guys. Yeah, I see.
Yeah.
Yeah, but we had the
my
discussion.
neck beard is down here. You just can't see it.
We had a discussion recently in few tickets about using virtual threads for Cassandra, especially to improve performance as well, because when you have a lot of blocking requests, you are spending a lot of resources for switching threads and packing and unpacking them. It's painful. So virtual thread can be helpful here as well as a way to improve performance too.
Yeah. But Asya, you bringing up like newer versions of Java also maybe is a good example of this reducing head of line blocking. So old Java had this head of line blocking problem with garbage collection, right? We would literally stop the world and then do all the work, and then you'd get this like second of tail latencies. new versions of Java are able to break the garbage collection process into these small chunks where there's very small windows where we have to block.
Yeah. Last version Shenandoah collector, supports such things. Exactly.
So, like, if you were to read how like Stop the World GC works and how Shenandoah works, like that is basically the implementation of reducing head of line blocking kind of technique for tail latency. And we see that right in the real world. Like if you run Java or you run Cassandra on newer versions like 21, you can actually see like a significant reduction in tail latency because of that. So that's actually probably the best example. The next one I find.
Hold this thought. Pragmatically speaking, since you both are from Cassandra, what does this translate to? Use Cassandra version no later than X, so that you use JVM 21, or?
So using 21 still requires some special setup right now. There are people who are doing it. Dimitri may be one of them. But
on the production.
Yeah, but to answer your question, Dima, if you are like deploying a new Cassandra deployment today, I would start with Cassandra 5 flat out. It at least supports Java 17. You get a bunch of goodies from that, but 5 also has a whole bunch of performance improvements and is stable.
Thank you.
So the next technique, again, I find very counterintuitive. I've never actually done this either, but Google did it, was successful, and that was actually to synchronize background work. So usually we talk about spreading or jittering background work. This paper talks about synchronizing it. And what they argue is that when you synchronize it, the impact window is limited and you know when it is. So like if you know you're always going to have an impact window at the top of the hour and you just sort of like accept it, it's better than having an impact throughout the hour. Again, I've never put that into practice. Most of my systems, I would say, are designed to accept that it's spread throughout the hour and to like use these other techniques around it. But I thought it's an interesting enough, like, and it makes you think from the paper that I wanted to call it out. But I do not have good examples of doing anything like that I can think of.
I have a real life example that is warranted here. Back in the early days of Google, it's going to be an offline example. Yeah. We had coffee machines on every floor, like at least 2 of them, on micro-kitchens. And every single coffee machine would go into self-maintenance, self-cleaning mode at the beginning of the hour. So the tail latency of getting coffee was plus extra 2 minutes if you happened to be there at the beginning of the hour. And like we used to joke as engineers that it's a stupid idea. These machines should add some random factor, random component, so that if you walk to a coffee machine and it's self-cleaning, the one next to it should be available, right? Otherwise, you form lines for no good reason. That's a perfect illustration.
But that's opposite. This is a problem. I also a bit confused by this example in the article that it says that you should synchronize your systems to have a kind of offline at the same time, and instead of spreading it across the time. It's what the paper suggests. Completely opposite idea, because I saw attempts to, for example, to do same thing like you mentioned about coffee machines for GC, for example, to try to trigger garbage collection on different nodes at different moment of times to avoid an outage, just forcing it or try to predict it and to introduce a jitter. But here the idea is let's have a short period of time when all of them are in maintenance, but then we don't have tail latency. If I got correctly the paper.
Yeah, that is the idea. Is like I think like on average your tail latencies will be lower because you're not experiencing this pain throughout like the day. It's just at one time. But yeah, Dima, your story makes me think of another offline example, which is when I have to have work done on my home, I schedule them all at once, so I feel the pain all at once and not spread out throughout the week. But I don't have good like Dima, I think like Dimitri, my intuition is that it's better to spread it out and then use the 2 techniques that we're about to talk about. And so these are the main techniques of the paper for single requests. And the first one is hedged requests. And this is a technique that I've seen used successfully for the majority of my career. The basic idea is a bit, again, counterintuitive, which is that if you have, let's say, multiple replicas for a database, or let's say you're working on like an API, so you have multiple instances of your API server behind a load balancer, you send the request to multiple machines instead of one, and you let them race to finish. And so on the surface, this is counterintuitive because you're telling the system to do more work. But the reason it works is because the probability of more than one machine experiencing an event that causes tail latency goes down versus a single machine. So if you were to like take this graph that's over here on our screen right now, but then you did it for the probability of hitting two machines instead of one machine, you would see the probabilities go down. And so that's the intuition behind hedging requests. Cassandra does this in production. We call it speculative retry. The systems at my job that live above Cassandra and provide APIs to the database do this as well. API servers in our systems do this as well. And again, the idea is just to basically like sort of brute force your way around this variability by saying that at least one of these will not have variability. Typically when you do hedging, you hedge to two, you do your primary request and then you hedge to your secondary request. It's rare that you would like hedge a third time. So it's typically just two requests. So you're doubling the work in some cases. In the naive case, you're doubling the work all the time. So like, let's say we're all replicas. I get the request. I send it to, Leah and Dima, and like every single request I get, I just duplicate to everybody. That literally doubles the work and is a little bit like naive. So what most hedging systems do is we're measuring our latency, right? We have metrics in our system. And so we know talking to Leah on average takes 100 milliseconds. Talking to Dima on average takes 105 milliseconds. And so when we send the request, let's say to Leah first, we wait some percentage of our expected P99 latency. So let's say our budget is 100 milliseconds, we wait 70 milliseconds. If after 70 milliseconds we haven't heard back from Leah, we send the request to Dima, and we're essentially hoping that Dima can answer the request in 30 milliseconds or less. And so the tuning of this becomes the challenge. The easiest thing is when you know you have an SLA. So you know that you've promised someone, like, I will complete these requests in 100 milliseconds in my P99. And you know what your average P99 is. So if you know your average P99 is 30 milliseconds, you can say, okay, fine, when I hit 50 milliseconds, I'm going to send the second request, because on average, that means my total worst case will be 80 milliseconds. So the hedging is done on a trigger. And again, it's usually done by a percentile. So like in Cassandra, you can say trigger speculative retry based on the P99 latency, etc. So this technique, super effective, on average brings down your tail latencies considerably because you're working around that variability, but it's not perfect. Any guesses on where this can go wrong?
Well, the failures are correlated.
Yes. So the way I would say it is if the request is expensive by nature, but also if the failures are correlated, right? So if the request, for example, causes the database to break, sending the request to another node will also just break that node, right? So that doesn't help. And that's kind of like the correlated failures like Dima is saying. But also if the request is literally expensive, like let's say you're an HTTP API, you're taking file uploads, and someone uploads a 30 gigabyte file via your HTTP API. If you send that to multiple places, you're just going to overload both nodes. In Cassandra, we see that like Cassandra is very good at reading like one key. It's not very good at reading like thousands of keys. And so we'll see that in Cassandra, that if we try to speculate and read thousands of keys, and then we send that to another node, what ends up happening is kind of this cascading failure around the cluster. So hedging is not good when the request is expensive, And I would say this is still an area of research. Like I've had 2 incidents in the last 12 to 18 months that have been the requests are too expensive and hedging exacerbated the problem. In talking with the Cassandra community, there are some people who have like ideas on how to fix this. Like you could imagine trying to get a sense of how expensive a query is and then using that to determine whether or not you should hedge. But the how expensive is a query is very difficult to answer accurately because by nature of answering that question, you have to start answering the query, and so that can be expensive. Similar, like in the HTTP API example, if you can, you know ahead of time the file's 30 gigabytes, so you could say like, oh, I'm not going to hedge this giant request or something like that. But in most cases, it can be a little bit too complicated.
The way
So
I internalized it back in the days is it's about the statistics of the requests latency. It's not about the median or average. It's about the statistic. If you have if you can predict that this request has a following distribution of latency, then you can say for 95th percentile, so one of 20, I'm going to hedge. That's healthy. But your prediction might be off, and then if you're off in the wrong direction, you're going to be over hedging. Yes.
Yeah, exactly. And in some cases, like if you're off in predicting the cost of a request, you're just going to be, again, knocking the system over. Any other questions on hedging? Just noting the time.
I just want to highlight a few things. First one, you can use hedging for server side as for client side. In Cassandra, it what happened. We have a speculative retry on the driver side as well as for server side, because if you have just speculating on the server side, you may still have a slow coordinate itself just because of GC, and still retry on the client side may be needed. So it's a kind of hierarchical thing, but at the same time, it can introduce even more overdoing, like you mentioned, in the system in total. So this kind of hierarchy, when we have a hierarchy within the system, it can create even more load. So you will have to pay for your availability by more CPU and other resources. That's the first thing which I wanted to mention. The second one, it's still like in Cassandra, I have found recently an issue with speculative retries about latency. Unfortunately, Cassandra measured the time to execute speculative retry. It uses the total request execution time instead of replica answering time as a threshold for the percentile, and it's actually introduces a kind of a negative feedback loop, because if you are doing it slow enough, your overall time is increasing, and next time you will do your hedging request later in time, and it's increasing and increasing up to almost timeout value. So
I think that highlights exactly what Dima was saying of like, if your metrics for this aren't good, your implementation will not work well. And I would say 20-30% of the time, I have to turn off hedging in Cassandra for certain workloads, like 20%, 30% of the workloads, because of those sorts of issues.
And I saw an opposite approach actually when people said, okay, availability for me is more important than amount of resources, and I will just trigger hedging immediately, not by base percentile, but I will just send 3 requests instead of 2. It will be overdoing, but I will get the best latency. So it's a kind of configurable trade-off, and you can sometimes choose another approach. And the last point, I've seen interesting researches in the question. Okay, I need to do initial request and then hedging. Which nodes should I select? Because the logic how to select the nodes, it's interesting topic by itself, because there are many algorithms, and it's still, I think, not ideal in Cassandra. How do we select replicas to query original queries as well as hedge one? We are using Snitch now, but it tends to introduce some issues as well. I will share a link to an article. It's about introducing some logic in Cassandra, but it wasn't introduced in Cassandra, but I found it implemented finally in Elasticsearch.
Oh, nice.
It's funny.
Yeah, if you could share that, Yeah, please. I'm interested to see that. And we'll actually talk about the snitch as we get to the end here. I'm going to quickly cover tied requests because this is another technique that I haven't seen used very much, although it kind of is like the work shedding that Dima mentioned. But the general idea is you kind of do what Dimitri's talking about, where you just hedge immediately. You just put the request on multiple nodes. But you have the ability for one node to tell the other node, hey, I finished the work. And so that will cancel the work on like the node that hasn't finished yet. And so the paper calls this tied request, but I actually have never seen an implementation of it. So I'm not going to spend too much time on it, but I just wanted to let people know like that's out there. I think the challenge you'd have with tied requests is getting the signal to the remote node fast enough. This works like when you're doing like map reduce jobs, right? Like you have these two things that are running for the order of like 20, 30 minutes. But it doesn't really work in like a HTTP API setting or a database setting or something like that. So I think this is a little bit specific to what Google was doing. So that covers
one
the
really
technique.
real quick comment must be made here. We're only talking about read requests here, or at least idempotent requests. If you can potentially, if it's a mutation request, you're not supposed to do it because you'll ultimately do double, triple the work.
Yeah, and you'll actually see in the paper, they just basically say like, what about mutations? And they give you a paragraph about it. And so they basically largely say that in most cases, write latency tends to not be a concern. In that like, even like with users' brains are sort of tuned to like changing things takes longer than getting things. We're impatient about getting things as humans, which probably says something, but so the techniques we talked about are what they call the single request techniques or within request techniques. The other set of techniques are what they call cross request techniques, or what I would call like per node techniques or per cluster techniques. So the first one they call micro-partitions. You might hear this as vnodes. This is more specific to database systems, but the idea is, let's say like you were sharding your data, so you're taking your data and you're bunching it into ranges. The naive way to do it is to say, if I have 10 computers, I'm going to have 10 ranges. The smarter way to do it is to say, if I'm going to have 10 computers, I'm going to have 100 ranges, and I'm going to assign those ranges across the 10 computers. This gives you a couple things. When one of the 10 computers fails, you now don't have to move the entire block somewhere else. You can move parts of the blocks to like the 9 other machines. So you get this failure tolerance. The second one is that you can deal with heterogeneous systems. So like what if of the 10 computers, one computer is larger than the other computer in terms of resources. So you can put more micro partitions on that computer. And in the chat, Dima called out consistent hashing. Consistent hashing is like the pinnacle algorithm for how you like place and move the data around, and it would take its own talk. So for the sake of time, we'll just mention it exists, and if folks are enjoying these and they'd like to do more, I'd be happy to do one on consistent hashing.
It also exists.
Yes.
But we can do it. We can do it again. We can do it again.
Okay. No. I'll go watch the one that you did. I love that. So micro partitioning is one. Another one is basically replicating more. So they call it selective replication because we need fancy terms. But the idea is basically to have more replicas, or like in an HTTPI case, this would just be like more nodes. But in a database, typically, let's say like I'd say in 95% of the cases, the industry uses 3 copies of the data. We use that as a balance of cost, performance, and availability. In some cases, however, it might make sense to have, let's say, 5 replicas of the data. That will make your writes slower, but it will give you more computers to service reads. And so that may be cheaper than, let's say, adding more machines and then just having like less data per machine that you have to pay for to get that same sort of performance. So you can think of selective replication as just more replication. And then the last technique goes into what Dimitri was sort of referencing with what we call it in Cassandra, the dynamic snitch. But the idea is, again, using metrics to determine which machines are having performance issues. So you're monitoring the performance, and load balancers do this all the time, right? So you have a load balancer in front of your HTTP API, like running on Kubernetes or something, and the load balancer is measuring the response times that it's getting. If it sees one of the nodes drift in response time, let's say be 20%, 30% slower than the other nodes, it stops sending it requests for a bit, or it sends it less requests for a bit, to like let it catch up and to not feel the effects of that slow node. And so that's what the probation is we have a period with which we don't send it requests, and then we try to start sending it requests again. There are a whole bunch of ways to do this, and there are a whole bunch of ways to shoot yourself in the foot doing this. And so Cassandra, for example, actually out of my employer over like a decade ago tried to make this smarter. And so what we tried to do is actually measure the background work happening on a machine. So Cassandra does background work. It's not important exactly what this means, but we compact data, we repair data, we do other kinds of like bookkeeping and housekeeping. And so we tried to measure the CPU load and then the amount of that background work that was queued up on the machine. That turns out to be very, very poor signals, in part because of what Dimitri just said, which is you're observing the past and you're observing and trying to also predict the future with the background work. And the heuristic has to be really, really good to rely on that. So
that's the beauty of being cross discipline, because like I'm a data scientist at heart, and that's effectively the multi-armed bandit problem, where you pay for information, and the more you pay, the better is your data. And then the leaky bucket abstraction that is most often used by routers, by load balancers, that's effectively one of the cleanest approximate solutions to this problem that is well researched in like ads. If you like the problem, which ads to show is doing exactly this. It's trying out on small traffic numbers to see which ads perform better. Exactly the same problem, like 1-to-1.
100%. Yeah, I love that parallel. And so what we found in Cassandra is just doing it the simple way is the best way. Just measure the node's latency. So we ripped out all that fancy stuff that wasn't actually very fancy, and we just look at node latency now. And then we also tuned the threshold. So we used to say a node had to be only 10% slower. We now say it has to be twice as slow by default as the other replicas. And then as Dimitri mentioned, there's this caveat of you also need to use the correct latencies that are representative of each node. But Dimitri, did you want to add something to that?
Yeah, with another issue, when you introduce in latency, at least what the current mechanism Cassandra does to reduce cost of this latency metrics calculation, you are doing it periodically. You are aggregating metrics, and then you are using like 90 or 50 percentile, I think it's 50 percentile now in Cassandra to order replicas. And the problem, if you are doing this kind of periodical recalculation algorithm, you have a delay the period of these recalculations. So you're still reacting to some metrics collected, aggregated in past, and you're using this old information to decide what you're going to do. And that's why the article which I mentioned previously, which is called C3, it's interesting because it tries to use some kind of streaming, more up-to-date real-time information about latency and some statistics about the latest request to decide how to balance, instead of this kind of periodical batching aggregation for metrics, which is always not accurate. And the second issue, this kind of relying on metrics implicitly introduces some kind of oscillation in the system when you are selecting some good replica to send requests more. And because you're sending requests more, the replica becoming slower. And as a result, it's on the next round, it will be less selective. It will be selected less frequently, and you will have this kind of periodic pattern of more load, less load, more load, less load introduced by this kind of algorithm. Not sure if I tried to explain it, but it's clear.
I mean, I think it's a complex topic, but I agree completely. And so
I followed, but it was not easy.
There's just a lot that can go wrong here. And then really quick, one technique that they talk about as a way to deal with this is what's called Canary requests. But basically, like, you can sort of send out a test request. Canary is a term typically used in deployments, but it's a similar idea of like, let's just send out a test request to see the latency. So that covers the techniques of what we call across requests, right? And they're across because like the latency induced probation is looking at the performance metrics across n requests, whereas hedging is something we do on a single request. We choose whether or not to hedge on a single request. Yes, we need metrics that are cross request to do it, but like the technique is applied to a single request. So these are the techniques that are discussed in the paper. As Dima mentioned, these are for idempotent or reads typically. There is a section here on writes that largely says like we're not talking about writes in this section, but there are some things you can do. But that they can be inherently tail tolerant just by like the nature of the implementation, right? So if we use a write algorithm that only needs a quorum or less than a quorum of requests, will be less latent in the tail than if we need like all of the replicas. I love this paper because again, I think, you know, it's over a decade old. It's about practical real world insights, and it's something that we can apply to our systems right away, whether it be again like a middle tier web service, a MapReduce system, a database, even on the front end, right? Like you can use things like hedging on the front end if you are like in multiple geolocations, right? So if you have a data center in the US and in EU, you can use hedging because like by default it would make sense to talk to the EU data center for your customers in Europe, but maybe there's something going on in that network path and you can get to the US data center faster and give them a better result. So these techniques are pretty ubiquitous across the engineering stack, as long as you're essentially doing something like networked or distributed. So with that, I'll wrap up here. I do have a stop at like 11 or just right after, but I'll open it up for any more questions or discussion with our last few minutes. And before I do that, I just want to say thank you all for attending and listening to me blab on for 57 minutes or so. It was very enjoyable, and thank you to the folks who participated as well in the discussion.
Thank you.
Thank you.
Any
Hey,
questions
I have
to
a quick
Jordan?
question.
David?
Yeah, can I ask a question?
Yeah. Go ahead,
I-
David.
So we have a hard stop in like
Well,
a few minutes, right, for you, Jordan?
Yeah, let's say 11:05. 8 minutes.
Okay, great. So I think Dimitri might have touched on this a little bit, but this, for example, like hedging and some of these techniques, we could introduce at various points in the stack, right? In the between the front end and the load balancer and an API and load balancer, and then the load balancer and the database. I guess, is there in your experience, have you seen something come up more often, more where it's more critical, or do you see that across the whole stack? And also, how do you slowly introduce this? Because I'm thinking about, our QA environment, whatever, it's not going to have users, using it. So, yeah, if you could touch on, I guess that's two
Like
questions.
the practical aspect. I think the question is, how do I practically deploy a technique like this? So I think I don't think I have an answer to like if one layer of the stack is more effective than the other. I think in the real world, it tends to come down to constraints. Like, for example, in my world, the reason like the application has hedging is they weren't making modifications to the database and they were hitting the problems like Dimitri and I have described with Cassandra's hedging. And so they needed the hedging at the upper layer to like work around that, but that was a constraint of like where they could write code, basically. On the other hand, there is like speculating at the in the Cassandra layer helps when a single Cassandra node is slow. Speculating at the client layer helps when a single Cassandra node is slow for different reasons. So like you really need both, like Dimitri mentioned, to like really get the full benefit out of it. And so you'll have to look at like sort of the conflation of all your like context to determine where it's better. But I'd say like there are easy places to start, like your load balancer or your database, because a lot of them just come with it built in, and it's more about turning it on. And then you could be like, oh, this is still something that's affecting me. I should spend like the engineering effort to fix this in my like application layer or something like that. And then, sorry, I'm forgetting the second part. Oh, QA, yeah. So I'd say for testing this, you are going to need some synthetic traffic. So when we tested this, we built load generators at the application layer that drove the application and caused this throughput issues. For Cassandra, we have pretty advanced load generation tooling as well that lets us test these things. Sorry, David. The last thing is you can also introduce artificial latency in like a test. So like you could have a test that only sends one request or two requests, and you like introduce a sleep in your test on the node and then like assert that hedging happens. And that'd be kind of like the unit or integration test that you'd write for something like this.
I want to add one thing real quick, because I think I know where you're coming from, David. So Jordan answered from Cassandra's perspective, and I think knowing what you're doing these days. So first of all, gRPC has hedging built into it since not too recent version. Second, we live in the world of client libraries and service meshes, and a service mesh is a good place to introduce hedging. Like that's a good level to introduce hedging at, because then it's not a developer problem, but the DevOps problem. And then, of course, all this issue that different distributions of traffic and latencies in QA and staging and production, that's no longer your issue. That's your DevOps issue. I mean, I'm not saying just dump it on them, but it's not something. If it's something that can be done in the configuration of your service mesh, it'd probably be better to be done there as opposed to your code, just for separation of concern reasons. And I think Dimitri has something to say. Nope.
No. Okay. Cool. Any other? We probably have time for maybe one more question before I go.
I was about to say the same.
Hi there, Jordan. Quick question. Like in regards with overhedging, right? You did say that we basically might be measuring something to understand overhedging, or any kind of variability of shared resources or daemon contributing to the problem. I just wanted to understand what are the right metrics to understand it's not a red herring situation, and we basically are measuring wrong metrics. So can you please highlight what are those right metrics to understand overhedging, and also
so in my opinion, this is a place where you want to like like we'd say like keep it simple, stupid, like KISS. Like I would just use the latency of the replicas. I think to Dima's point, the like trying to use metrics like CPU, memory usage, all those other things devolves into a very complicated, basically like ML problem. And you won't get a good enough signal where you'll constantly have problems. So my personal opinion is, and this is where I was one of the folks that moved Cassandra back to this, is that you just use the latencies, because that is the measurable thing that you're actually trying to operate on anyways. Is it perfect? No, but it is very, very simple to implement, very, very simple to understand, and is better than some of the more complex ways you could approach it.
got it.
Great. Charles Polsky had a wonderful article, like evidence-based scheduling for human tasks. You're talking about evidence-based latency prediction for past requests, like future requests based on past requests. Yes, simple things work.
Cool. Well, I will wrap it up here. I'll let you all keep discussing if you want. Thank you again for having me and the participation. I really enjoy doing these and talking about papers, and especially like how these academic papers can be applied in the real world is a passion of mine. So thank you. And Dima, thank you for the invite in the forum.
Thanks, Jordan. I'll stop the recording,
Thank you.
and then we can talk offline for a bit. Thank you, folks.
Cool. Thank you all. I'm going to drop off.
Dima, back to you.